how does a machine actually make a decision, when it comes down to a simple choice? Well, today we're going to pull back the curtain on one of the coolest and most intuitive tools out there for doing just that, the decision tree. Let's get right into it.
All right, to kick things off, let me ask you something. Have you ever played the game 20 Questions? You know, the one where you try to guess what someone's thinking of just by asking a bunch of simple yes or no questions? Ring a bell? Well, believe it or not, that super simple game, it's pretty much the perfect way to understand exactly how a decision tree works. Okay, so check this out. Imagine we're trying to figure out what animal we're looking at. Is it a hawk, a penguin, a dolphin, or a bear? This little diagram here, it's just a visual version of that 20 questions game. And that whole process, asking a simple question, getting an answer, and then asking another one to narrow things down, that is the absolute core idea behind a decision tree. So let's trace the logic, right? We start with a big, broad question. Does it have feathers? If the answer is yes, well, now we're down to just two options, a hawk or a penguin. So our next question is obvious. Can it fly? But what if the answer to that first question was no? Then we go down a totally different path, and we might ask, okay, does it have fins to tell the difference between a dolphin and a bear? See how that works? Every single question just slices our list of possibilities. Okay, that was fun. Now let's get a little more formal and see how this simple game translates into the actual structure used in data science and machine learning. So this is what it looks like when we put on our data science hats. That game we just played gets turned into this branching structure. In the world of machine learning, this is what we call a decision tree. And trust me, every single piece of it has a specific name and a job to do. Let's break down the anatomy here. That very first question we ask, like, has feathers, that's called the root node. It's where everything starts. Then all those follow-up questions, those are the internal nodes. The answers to those questions, the yes or no, those are the branches that lead us down different paths. And finally, when we get to the actual answer, the hawk, the penguin, whatever it is, we call those the leaf nodes. See, it really is just our game, but with some fancier terminology. But this brings up the most important question of all. When we play 20 questions, we use our intuition, right? We kind of feel what the best question to ask next is, but a computer doesn't have intuition. So how does a machine figure it out? Yeah, exactly. Imagine you have a massive data set with thousands of rows and maybe hundreds of different features you could ask about. How on earth does the algorithm know which question is the best one to start with? Which question is going to give it the most bang for its buck and split the data in the most effective way? Well, the answer, believe it or not, lies in a really powerful mathematical idea. It's all about a quest for something called purity. Just imagine your data starts out looking like this, a total mess, right? A jumble of blue circles and red triangles all mixed together. The algorithm's entire goal is to find one single question that can slice this messy group into new, smaller groups that are as pure as possible. And by pure, I mean a group that's mostly or even completely made up of just one thing, just circles or just triangles. So how does an algorithm actually measure messiness? It can't just look at it and say, yep, that's messy. It needs a number, and for that, it uses a concept called entropy. Honestly, you can just think of entropy as a score for how much chaos or disorder or uncertainty is in your data. So, for example, a data set that's a perfect 50-50 split, like a coin flip, has the highest possible entropy. It's total chaos. You have no idea what you're going to get. But a data set that's made up of only one thing, that has an entropy of 0. It's perfectly pure. So the whole game for the algorithm is to find questions that drive that entropy score as low as possible. And this leads us to the key metric, the thing that drives the whole process: information gain. It sounds complicated, but it's not. Information gain is just the measurement of how much a question reduces that entropy score. So the algorithm literally calculates the information gain for every single question it could possibly ask. And then it just picks the one with the highest score. That's how it builds the tree. Okay, that's enough theory for now. Let's make this stuff real. We're going to build a decision tree from scratch using a super simple example. All right, here's our tiny little data set. We've only got two features to worry about, the weather and the temperature. And our goal is simple: predict the outcome. Are we going to play football? Yes or no? Okay, first step, let's measure how messy our data is right at the start. If you look, we've got 2 yes answers and 2 no answers. That's a perfect 50-50 split. In the world of entropy math, that perfect chaos gets the highest possible score, 1.0. Now the algorithm starts testing its options. It says, okay, what happens if I split the data based on the weather?
Well, if it's sunny, we're left with one yes and one no. And if it's rainy, same thing. One yes and one no. The new groups are just as messy as the one we started with. So our information gain is zero. This question is totally useless to us.
Okay, so scratch that one. But what happens if we split by temperature instead? Now take a look at this. When the temperature is hot, we only get no answers. And when it's cool, we only get yes answers. This is amazing. Both of our new groups are completely pure. Their entropy score is 0.
So that means the information gain for asking about temperature is a whopping 1.0. We went from maximum chaos to perfect order in just one step. That makes it the hands-down winner. That's going to be our first question, our root node. And there you have it, our finished, beautiful little decision tree. It's so simple. All it does is ask about the temperature. If it's hot, we don't play. If it's cool, we do. And the coolest part? The algorithm figured this out all by itself just by using math to find the question that created the most order. So, if there's one thing to take away from all this, it's this. Decision trees are not magic. They're really just a clever, automated process for finding the most powerful questions to ask. They use the math of entropy and information gain to find order in all the chaos. But this does leave us with one last, really interesting question. What happens when a tree gets too good at asking questions? What if it gets so complex that it asks a million tiny specific questions, and instead of learning the real pattern in the data, it just ends up memorizing every single example it was shown? Well, that's a problem for another day.